Okay, so this is my explanation video for the very first presentation video. Um, we're given a strain rosette that is shown on this piece of paper. And basically what a strain rosette is a compilation of strain gauges, which are small little readers that have a resistor in them, an electric current flowing through them. And so basically what they do is if you were to put a strain gauge on this card here, and you're to apply some sort of stress and pull this, the deformation in the card would be read by the gauge because it would also deform and the resistance within that gauge would change with the deformation, and a computer attached to that gauge would then calculate the change in resistance, and that would then give you these values of strain. And then when you find those, it's important to find the strains in the x and y axes. So to do that, we are given a couple of strain equations, and they go as follows. Strain A equals strain of x cos strain plus shear cos theta A. And now all the other equations are the same. They're just, you just change out the A with B, B with C, so on and so forth. The big thing about these, as you can tell, is you can find the strain within the x and y direction, but you could also find the shear strain as well, which will be very helpful for the next step of this presentation. So from this, you can then deduce that, so if you look at EA here, it would equal this gauge right here. And for the angle, it's important to use the x-axis as a reference. So if you just go down this way, you obviously cannot use 75 degrees, that would be off. So what I did was I used this angle here, which is 285 degrees. You could do negative 75 as well. I just like keeping everything positive. So when you start using that angle, you get this. Mu inches per inch. And this is another very important thing. You can see that the strain gauge 2 is already on the x-axis. So that helps out a lot because that just tells you that this strain then becomes strain on that axis. So when you come down to this equation here, all you have to write is 200 inches per inch cos squared of 285. Now this is the one you got to be looking for since it isn't given in the problem statement. And along with the shear, 285 sine 285. And at the end of it all, this then boils down to negative 313.397 inch per inch, 0.933 sec y, it's y times negative 0.25. Alright, so that's the first equation, and now we obviously can't solve either of these with just one equation, so we've got to use the next one, which would be for this strain gauge, seeing as we already know what the x is, what 2b would just equal 200. And this comes out to being 420 equals 275 degrees. And at the end of this, what you get is 11.6 inches per inch. Plus 0.25 xy. And this is an important thing to realize why you had to make sure your angle is either 285 or negative 75. As you can see, the right hand of each equation is the same except for this negative sign. So if you hadn't done this, it just would have been the same and you would have gotten the wrong answers. And then from these two equations, you can balance them out, isolate and solve for either EY or sig y or the shear strain. And then after doing that, you get the values of EX, which you already had, 200 inches per inch. EY, I'm doing the math, 52.65 inch per inch. Inch per inch. Alright, the next part, we're going to have to use Moore's circle. So here I used Moore's strain circle, which is exactly the same as Moore's stress circle, but the biggest difference is when you look at the axes, when you have strain here and you're looking for shear, it's important to make it half of this given value right here. Because if you don't do this, then everything will be off and you won't get the right answers. So from there, you can plot your graph. Go like such. So put these down here. This would equal 725. And this axis is like so. This axis is like so. And down here, negative 725. Let's move this up a little. And now, this is the important part about Moore's circle, is properly placing all your points, properly drawing out the right diameter. So the first step that you want to do is plot your two strain points using your EX and EY values. So the general method is for your EX value, which would be say around like here, you want to bring that down and make that your point. Have it relate with the negative shear. So this would be 200. And then for your Y, you'll relate that with a positive here, 52.65. And the next job is you connect these dots like so. When you do this, you can find your center point here. So the way I did that, you just do 200 minus 52.65. That then equals 147.38. I'm sorry, video cut out. Didn't mean for that to happen, but as I was saying, when you get to this point here, you get a value of 73.675. Yep. And that is this distance here. Call it D. There goes D. Then after finding that, you can add it to, say, this value. You could also subtract it from this, but I'll add it to this. So 52.65 plus this here. That then gives you your center point, which equals, what is that? 126.3. So 126.3. Then after finding that value there, it's very important. You can go around here and start drawing your circle. Try to make this as nice as possible. somewhat decent. Then after doing so, you need to find the radius of this circle here, which would equal right here up until the center point. And to do so, move this up. The radius then equals square root of that d value. Actually, I'll change it to r, small r. Make it small radius. Makes a bit more sense. You add that with, you obviously have here, and you got to add this value here, 725, using Pythagorean's theorem here to get the hypotenuse. And at the end of it, you get a value of 728. Now, inch per inch. Now, this is a very helpful number because it allows you to find your max shear stress. And as you can see, you got to remember that on this axis it's divided by 2. And from the last thing, max over 2 equals r. Thus, this equals 728 times 2. And then you get a value of 1,456 radians. And that is your max. And now to find your principal strains, which are quite important as well, use this equation over here of your center plus and then minus your big R here. And so basically what principal strains are is strains found on the principal, it would be the principal plane, and this plane is a plane where there is absolutely no shear strain, and this allows you to find the maximum strain that your object, say it's this card, will endure from the applied stresses. Because say if it was at some different kind of angle on a different plane, there would be shear stress involved, and then you couldn't find the maximum and minimum of your strains and whatnot. So we get to that point. For 126.3, add the radius, so you get a value of 855 inches per inches, and then here get 126.3 minus 728 equals negative 602.4. So now these here are your principal strains, and these are essential in being able to find what we're looking for, the principal stresses. And in order to do so, we got to use generalized Hooke's laws. And basically all that is a set of equations given to us to transform the strains we had been given and to turn them into stresses, so we can find the stresses that caused the given strains. So, another thing that goes along with that, very important to know, is you're going to need 3 things primarily. You're going to need the modulus of rigidity, you're going to need the modulus of elasticity, and Poisson's ratio. So 2 of these values I was able to find in the book. The modulus, I believe this can also be called shear modulus as well, because it has to do with the shear stiffness of the object, so it's kind of intolerance or its resistance to elastic deformations and shearing. And this value you get, this is also denoted as G, big G. This equals 10.8 PSI. And then you can also find the modulus of elasticity in the book. And this is just regular stresses. It has to do with the its resistance to elastic deformations for just normal stresses, not shear. So, and this is given E equals 28 10 to the 6. Now that we're given these, we can find Poisson's ratio with a given equation. That equation is the modulus of rigidity equals modulus of elasticity over 2 times sum of 1 plus Poisson's ratio. So plugging in the values that we have, you get 10.8 times 10 to the 6 equals 21. Then after solving out, you'll find that this value equals 0.296, and you'll notice that it is it's dimensionless. It has no prefix or anything, and that's because what Poisson's ratio is, it's so say you were to deform this, the restraints on this, it's the ratio between the strain that can be found in this axis and this axis. So the change in length of this card, the ratio of this change to this change, that's Poisson's ratio. So once you find these equations, you can then use the generalized Hooke's law, and the equation looks something like this. So for the first principal stress, equals E 1 minus Poisson's ratio, principal strain, minimum principal, and then this just equals to the -6. These are the values we got from back here, as you can see. So then after you have figured that out, you can then deduce that first, your maximum principal stress equals 28,567 pni, which then can be turned into 20.8 ksi. So that's your max. And then now for your minimum, it's basically the same equation. Instead here, it's 2 plus I messed up here actually. It's obviously not the value, it is sorry about that. Down here, 2. And after doing all the math, you'll get this to equal negative PSI, which then just equals 1.7 KSI. And now that you have your max and minimum normal stresses, it's important also to find your maximum shear stress, and that just equals the modulus of rigidity times maximum strain, shear strain, sorry. Let's do that. You can find that maximum shear strain equals 15.7 KSI. And so there you have all the values that have been asked for you. It is also important to realize that these principal stresses occur just like the principal strains occur on a different on the principal plane, which is different from the shear plane. So just know that all of this isn't happening at the same time. Thank you. And it is also important, sorry I forgot this part, you can see how there's two different values here, right? One is positive, one's negative. For this to be positive, that signifies that on the given plane, the principal plane, the maximum normal stress this can take is 20.8 in tension, so it's pulling against this, so like the force going this way. And then for this negative value, it's the minimum, but it's just in compression. It's important to note that, say if this negative value was higher than your maximum value, just in the negative direction, that doesn't matter. It just means that there's more compression than there is tension. Thank you.